Thank you for all for joining onto the webinar for efficiently for electric motors using AFP. My name is Pravin. I will be presenting mainly based on the literature and our own practices, what we know about efficiently producing sleeve for electric motors. A brief about myself and at Composites. I have been mainly working with satellite and launch vehicle structures to begin with. In recent years, I have been mostly working with AFP system with thermosets and thermoplastic materials. And now it's been like about 12 years working in composites industry. And at Composites is a provider of fiber placement systems that can think, and also we offer continuous fiber 3D printing. So with that brief introduction, let's dive into today's topic. To start with, we will go and start to understand why there is such a huge demand for electric motors today, and with that core principle of demand, why sleeve is such an important component. What are the key design consideration when we are thinking of designing the sleeves, the present ways of manufacturing these sleeves, the challenges associated with it, and the AFP approach and what the new AFP approach brings to sleeve manufacturing, and then diving into the benefits and how can you set up your sleeve manufacturing process today. So that's going to be mainly the purpose or the structure that we will go through. So let's start with the first step. So electric vehicles are growing in number very rapidly, and electric motors are basically the conversion engine that converts the stored electrical energy into the motion on the wheels. And you would want as much conversion as possible at the highest speed uh, possible, because you would want to get faster to certain places. And that's where at the moment we see the highest, I would say, the growing demand for the electric motors, which needs to be efficient. The I think the main factor driving, I believe, is the sustainability in the transportation that people desire in today's age. There are two types of motors that are used in the EVs of today, or prevalent commercially, I would say, used. Is permanent magnet motors and the induction motors. The permanent magnet motors, as the name suggests, uses the pre-magnetized component. They are already magnetic in nature and are put around the rotor. Uh, Whereas for the induction motors, the electric field is applied to create magnetic field around the simple metal. Um, as you can assume, as we are not consuming power to create magnetism, the permanent magnet motors are the most efficient, more efficient version of the of of the two. Induction motors, they have their pluses, and we'll come to that, but they are not as efficient as permanent magnet motors. Permanent magnet motors, to what I have understood from literature, are also very high in power density, torque density, and operate much quieter. The challenges associated with the permanent magnet motors are that the magnets and more rare earth metals that are controlled predominantly today by one country, that creates geopolitical tension. So it's not maybe the ideal solution to stick with or put all of the eggs in the one basket. And this, I would say, supply demand creates a dynamic that makes the magnets expensive relative to the induction motors. So there's the economic plus and minus to be taken into account, stresses, and you start to see, okay, why composites sleeves start to make sense. So the electric motor sleeves, the main purpose why they were brought into the picture is to hold the magnets in place while the motor is in operation. These motors are running at much higher RPMs, and these magnets, though lesser in weight, the momentum created by the high speed of rotation is so significant that it can easily break through metal sleeves at higher RPM. Thus, you would want to have metal sleeve that are able to hold the magnet in the position at the highest rated rotation speed. So the efficient operation means to have them not shifting. Um, One of the key concerns to start these was to have like the, so once you start to make them thinner, the safety concerns start to rise up. The rest of the um, sleeve considerations really comes from that if the magnet is not kept in place, it would be uh, creating all different types of losses that would turn into heat, and that would turn um, kind of create a cycle of failure that could demagnetize, accelerated demagnetization of the permanent magnets, to loss of energy, to safety concerns, or yeah, disintegration. So that kind of puts the sleeves in perspective, what's their main function is in an electric motor. So going into the materials, um, to begin with, when the motors were initially conceived, I believe it was metals where they started, and the operations were not at such higher RPM. So the main, still predominantly used in many of the industries, sleeves are stainless steel. For slightly premium application, Inconels and titanium sleeves, despite their difficulty of manufacturing, they are metal. Most of the mechanical engineer understand metal, so they tend to go for difficult to manufacture yet slightly less denser metal with higher strength. The key advantage, I believe, based on literature as well as to choose the metal, is to make kind of have match the coefficient of thermal expansion. So if there is going to be heat generated during the high speed rotation, the magnet and the sleeve would expand at the same expansion ratio, thus not disintegrating uh, and holding it together well. However, what ends up happening because of the higher density of the metal uh, at higher rotation, the self-induced stress is so high of just a sleeve alone that it start to expand, thus moving the magnet away from the magnetic field, the right placement, thus creating losses and creating more heat and kind of cycling it to having either very inefficient motor operation or having the failure possibilities. And there is the, I think one of the other factors is the conductivity. So in case there is some electric current that ends up touching, it could cause the sudden failure of the system as well, of the motor. Thus, I believe carbon fiber, as they were gaining in popularity, were tried because of their this lower density, higher modulus properties. At such higher speeds, having lower density basically means much lower inertia of rotation, thus much lower self-induced stress. And so that allows you to go for much higher RPM of operation. And at much higher RPM, being the high modulus, high strength carbon fiber, it's able to take up much more load, still retaining the magnet in place, allowing for efficient operation of the motor. Yeah, I believe that's kind of covers why uh, the whole industry would like to move to the carbon fiber side of sleeves. And as people knowing of composites industry, we know the cost and the manufacturing difficulty associated is the one that is preventing the move to happen. So by this point, we understood why we need more motors, why we need them to have good sleeves, and then what is the best material for the sleeve is. Um, Now, as we move towards designing the sleeves, we would want to have to consider what stresses and I would say operational parameters while selecting the material thicknesses given the application scenario. So, based on the literature, what I have found, it's the first and foremost is the hoop stress at higher RPM that creeps in and kind of pushes out any contender that does not have very high strength along the radial or the hoop direction. Yeah. Um, the I would say the magnetic assembly is you would want to have it assembled in a way that it is uh, press fitted or in a way it's not allowing it to easily lift off. It's just better to say a kind of a chambered design that does not allow. It's kind of one of the most common approach, and there are as you start to assemble the motors, you would want to have press pre-stress applied. So you, as we know, the motor will be rotating at certain RPM. We would need to have uh, the stress applied prior, thus negating it for the natural rotation speed. There are about 4 to 5 methods for applying these pre-stress, and there are hydraulic presses to additional sleeves to. A sleeve is one of the approaches, but there are other approaches too that can help with applying this pre-stress. And we'll come to the AFP part of the process, and we'll get to this pre-stress application. This is where uh, the AFP approach shines a lot, because you're able to apply the pre-stress at the manufacturing straight in one single shot. The next component to consider is rotordynamic, especially having the bending stiffness of the rotor hub, which in case of any imbalance faces the most amount of stress. I have found literature where carbon fiber um, rotor shafts have been also considered, but they do not add too much value, because they are not at the circumference level, so the stress levels are not that high. um yeah. Thermal and electromagnetic considerations are one of the kind of the downsides on the carbon composite side to make sleeves, because metals are slightly better in, I believe, the if there is any heat that is created from the rotation, metals are more conductive than composites. But electromagnetically, um, carbon fiber, I think it's is better, allowing lesser loss of flux. um, and there are a few considerations: thinner sleeve plus the materials property itself. um, but given the application, looking into each of these parameters gives the ideal candidate for the possible manufacturing method, material, and approach to produce. So I think this is one of the other chart that I feel is very critical to understand even more so why non-metallic makes a lot more sense. So getting into the understanding, the first key factor is there is higher strength and then the density, and both play the role to move the needle towards composites. So here the example data that I could find was for carbon fiber T700 and structural steel and titanium alloys. And the main um, s- component to look at is the specific modulus and tensile strength. Those both shine compared to all the other metal. I think specific modulus is almost invisible for metals compared to carbon. And this is the place where the carbon can be playing to its strength, because it can be applied directionally. Um, Going to the next stage is the and going beyond the material strength and modulus properties, corrosion resistant, um, and the ability to be in multiple environments is one of the key factors for longer uh, operation. So over the years, you don't need to look into the under the motor, because even if there is some moisture creeped in, there is no way there's going to be any rust. Um, Composites are very good for vibrations as well, and as you're running at such higher rotation speeds, you're trying to make sure that you're staying away from the natural frequencies. And the last point that I want to bring in this slide is to, once you design efficiently, composite sleeve are very cost competitive. even compared to very low cost metal, because the efficiency gain that you would continuously gain by placing a motor with higher efficiency is way beyond the just cost of raw material per kilogram goes. Thus, I believe this is why, um, in addition to all the factors now we considered, I think this kind of puts the foot down and says, yeah, composites. The present scope, if you would want to manufacture composite sleeves, so these are the, from some blogs, some literatures, what manufacturing methods I could pull together. There are direct wound carbon fiber sleeves, and so here we are talking either filament winding, or it could be AFP wound as well, thermoset, thermoplastic, anything that is directly wound onto the rotor. The second one is pressed on sleeves, which are, I would say, if you have already manufactured a sleeve that is constrained fit, and then you use some sort of equipment to put the sleeve on top. And this is considered the best in terms of being able to apply um, highest amount of pre-stress onto the magnets. And as we discussed previously, you would want to have very high amount of pre-stress, and this is assuming the magnet and the assembly is able to hold itself together and not crash on its own. Um, but this is the method that allows for very good amount of pre-stress. And then heat shrunk wound polyester, I would think this method is mentioned more casually in literature. Thus, I feel it's not, because it's not purely composites, but it's one of the low cost methods that was very primitively used previously. As you can see, it's not at all adds to the value. So by this time, we have understood why sleeve, with what material, and what are the present manufacturing approaches to this. And now I think serving to the title of the webinar, the direct sleeve winding with the AFP approach. So here, the title speaks a lot. First step is high tension, and then I would focus on thermoplastic composites. So let's focus on like how we define this process, and that kind of speaks to all of the key obstacles that we saw earlier. So this is the process is just placing thermoplastic tapes onto the magnetic motor or generator with significant tension. And once we say significant, it's you would want it to be as high as the rotor assembly can take. And if you focus on the heat part, what I'm showcasing here in these three images is the flash lamp heat technology. You can have laser, you can have hydrogen, you can just have normal IR, and all these basically just kind of different types of heat inputs. But what are the key consideration when you're doing the high tension winding with thermoplastics is you would want the thermoplastic to bond to the previously wound uh, ring or hoop. And to achieve that at such high tension, you want to make sure that the thermoplastic is at the ideal melt point temperature. So at this point, you don't want to have also the excessive heat, because you would not want the magnet to, if there is more heat, it just accelerate the demagnetization. So you would really want to consider how you focus or place the heat at the nip point. The second thing is choosing the right material. So you can choose a material that absorbs heat better, and that basically is the chemistry and the people joining from the material side. Um, for this application needs to really focus on a material that heats up quickly, cools quickly, with whatever additive in the polymer, because I just as a material, carbon is quite good uh, in doing so. And the uniformity is key in the sense that you don't want to burn the incoming tape or the substrate. You would want to really optimize for the, as it's a um, kind of a two circles or two circular geometries touching each other. There is almost like a nip point tangent where you would want to align your heating system so that you are able to place it almost in the middle, so allowing equal heat distribution. So you are able to run at the highest speed, highest pretension, and without burning either or tape or the substrate hoop. So this is where I would focus and call it uh, the heat part of the equation. Why having a good heat source that you can control fast, align well matters. Um, the second part of the title suggests this tension. And as we discussed, the pre stress on the magnetic assembly that can be applied is very, very critical. And the tension in the AFP or similar system basically can be increased to much higher degree by certain approaches. So, as shown in the image here, uh, you can just go through all the guide rollers and hoop through, and just the friction on those really allows you to add up tension. The more the rollers, the more tension there is. But with AFPs, usually the area that you have is quite small. So usually the tensioning is motorized. So you have a motor that is holding the material spool that is acting as a brake. And then in addition to that, along the way you definitely have hoops and pinch points where you're applying additional braking. And this basically the tension is kind of additive in nature and adds up to a final tension of certain newtons. There are pneumatic tensioner as well, but it's not that prevalently used. They are, I would say, just kind of friction adder in a way. So I would rather focus on the other section, which is the dancer and the clamping points. So once you are doing the continuous tape winding with high tension, the dancer becomes in a way obsolete. But as you would reach the either edge uh, of the cylinder of the motor, the turning would require the rotation of the winding axis to slow down and then increase in speed. And the dancer plays a key role to maintaining tension as there is a change in velocity, and it's a very critical component to consider. And I think clamping is more to help with continuously being able to do more. So not only do one winding and then manually change things, but with clamping you can hold much higher tension to begin with and then repeat the process continuously. But regardless, so these are like typical methods of adding tension, and it's not that challenging to increase the tension if you have the um, positioner and the robot capable of uh, holding that much load. Yeah, and range of tension that you would want to apply is controlled by three main factors. And this is just me trying to do some calculation and figure out, okay, so first is material, how thick, how wide your tape is, what fiber and matrix does it have, and then because it's thermoplastic tape, it's basically cured composites. So you can calculate how much along the length direction tension it can take, and the material put sets a limit. Then the second limit comes from once you apply the temperature, there is going to be melted matrix at the nip point, and that reduces the strength that the tape would be able to take. So this puts the bar of the how much high tension you can apply to slightly lower. And then the last point is you not want always to be tensioning too much, because there are certain applications that does not require too high of an RPM. So you always want to check with the application what are the hoop stresses coming and see what pre-tension makes sense, because yeah, doesn't need to be in very high pre-tension for no good reason. So even if your material applied temperature can handle much higher tension, you still want to check with your application that will give you much, I would say, higher speed of winding, and not damaging the material while winding. Yeah. So now we covered, I believe, the AFP process where we focused on the high tension thermoplastic winding, and why it's how it can be done, what are critical factors there. The next bit that is uh, put here is like why it is good to use this direct winding approach and what does it bring to the table. So you're basically doing like a very high tension winding, so you're getting the obvious benefit of pre-tensioning as you manufacture. Whereas if you're doing the two-step approach, which was mentioned as a sleeve and a press fit approach, so you make a sleeve and then you have a hydraulic system that applies. So it's like a two-step process. So whereas with this AFP direct winding, you have only one-step process, and that's it. I think also that's kind of the one of the reason to have thermoplastics is because you don't want to make it a two-step process. You want it to be in situ consolidated, cured, coming out, right? Pre-tension onto the rotor, nowhere else. So that's the ideal goal. Um, there are approaches that you can apply using the how you place the material, and how much you are able to have, I think, enhanced radial compression. um, yeah, you can choose materials, very high modulus material and very high strength polymer put together to get to the point. um, because also in this case we are building layer by layer, we can get to much bigger motor sizes because there's no limit to how thick sleeves we can do. um Thermoplastics are very good in terms of the um or yeah, I think just the AFP, the composites themselves are quite good with the water absorption. um and I think that's kind of the obvious point once again, AFP being the automated composites manufacturing method. You are able to be sure once you have set up the process, you can repeat consistently at higher rate without worrying that there is going to be variation in the process. Um, yeah, and there is no post heating required because as you use thermoplastics, there is a lot of benefits of using so. Once again, I have the I think I kind of covered this in the previous slide, but I wanted to just focus on why thermoplastic uh, specifically, because that could have been thermoset, and most of the properties could be true, and there could be like thermoset could be definitely one option where a two-step process of post curing is okay. Um, with thermosets, what you cannot do is apply very high tension because the material or the tape is uncured, and the fiber is the only thing that is taking the load. So there is very high chances of fiber breakage. So thermoplastic tapes can take much higher tension compared to thermosets. Thermoplastics are more durable for extreme environments. So that kind of makes them the ideal candidate for oil and gas industries and outdoor applications. Um, yeah, this is based off literature. The without the heat loss of like metal, but they have better modulus and low residual stresses. As I mentioned, no post processing because in situ consolidation is definitely possible. And I think the last one is the best thing, I think, which is driving now the thermoplastic adoption highly, is their reproducibility. So once you are able to reach the end of the life of the motor, those leaves can be repurposed to make something else. That's those need to be burned. Yeah. So overall, at this point, we are pretty much at the end of the webinar. But let's revise. We started with why do we need high performance motor, because there are more electric cars, and why do we need really good sleeves, because we want them to be efficient at higher speeds, and these sleeves are predominantly made with metal, but now more and more so with composites. Still very less percentage, but increasingly so. And what are the approaches and what is the key factor is the applying the pre-stress that would hold the magnet in place, and the processes that we discussed that was followed by the AFP thermoplastic winding process, and the benefits of just AFP and then thermoplastic as material. So now if you would want to set it up yourself, the this setup, what would be the requirements, what would you need to have, and where should you start? So what do you need if you want to set up the production facility is, I feel, just a robot. um, with If you have a chuck in front of it, great, but you can always buy an extra motor, and that is as good. So you have a robot with this rotating axis in front of it, and then you can just have the FP head that can be rented from either or, and then from at composites or from, and then if you need here that you would like to use, it could be of your choice. So you can use any existing heaters, or you can choose to have uh, some industry specific heaters that you would like to focus on, and I think that is where we can help. Then I think if you know what industry you want to aim for, where these sleeves will be useful, selecting the right material sets the price point, basically. Um, and design and simulation is where we can help with estimating the time and material used for the given material. And to help with also, I think, what would be the cost per cycle of making one sleeve could be very easily calculated. Yeah, but I think the first step usually, I usually say is simulation is always the cheapest and the best, because you can already show with very close to real numbers what would be the production speed and what would be the um, production would look like in a virtual environment. And it kind of gets a very good image of the um, of the setup, how the production setup would go to the customer's head, and then they could start with initial pilots already. But yeah, I think that's that's where I would say it's like kind of one of the last bit I would leave you with is, um, and I think this is one of the things that um, it's I think this is definitely the last slide, but the real life use case is who is using them at the moment. And this is the most famous use case I think out there, is the Model S Plaid from Tesla. And that's supposed to be one of the highest performing car in terms of speed, range, and acceleration, and to operate at such efficiency, um, where I think, and they have usually been very agnostic, but Tesla, which is very cost conscious company, have chosen carbon fiber sleeves. So it's kind of is an example of why um for electric motor sleeves will be carbon fiber sleeves with thermoplastic, which have very high tension. It could be with AFP or winding, but in the end, the seems like the application case is there. It makes budget sense in scale. There are other, I think, based out of a few other webinar information that I could find. There's also jet engine in planes that are for electric sleeves. They are thinking of using it. Subsea motors, but I couldn't find any specific examples. Um, yeah, I think except for if it's the same circular geometry, there are pipes, the hybrid pipes that are using it, but not in very high volume. Yeah. So I think with this, I would say we move towards the Q&A of the presentation. Um, Let me try to go to chat and see if there are questions. So let's see. High tension is mentioned during the direct sleeve winding. Can you provide, I think, precise order of magnitude of this tension? Okay. So please, I think, let the question come in. First of all, I think Jean, I think really thank you for the question. What I have found, given different application, you're looking from 100 Newton to up to 2000 Newton. There is a very high range, but it's the application that is deciding in the range of that. And with the FP systems, with motorized braking, there is a very high possibility the to change to what range you want to have. So it's just a selection of the braking motor that you would want to change, and then yeah, that would give you a very good range of tension. I would say usually be on the safer side, at least 1000 to 1500 Newton uh, system that should be taken, and then the uh, I think it should be sufficient for most applications out there. shouldn't create any other issue. I'm trying to see if there are more questions. Yeah. Okay. There is another question. Are carbon fibers the only material which can be used for composite sleeve, or there can be other fibers too, considering their material properties? I believe the glass fibers are very good candidates, especially the high strength, high modulus fibers. On glass, also, there is basically no limit. I think they may be even better in terms of how, uh, electrical conductivity, or sorry, the transparency for magnetic flux is considered. So uh, I think glass fiber is definitely a very good candidate. And one of the good thing is the system that you build is definitely not only suitable for carbon. It's just glass or any other fiber that you would find suitable in tape format would be able to create. Okay. I have There's a question here. Hi. Okay, somebody advertising. Yeah, there is somebody trying to promote us their thermoplastic material. Yeah, but it seems materials definitely quite useful. What is the matrix system that can be used? Could it be polyfins or more technical polymers? Stefan, I think it would be mostly any thermoplastic that you would know, like a processing temperature, and you can find in tape format. So some manufacturers selling them. I don't think so there is any limitations. Just from the application point of view, what I have seen is you would want to have polymers that are able to take higher temperatures, because the operation during operations, this motor can go, even though there is cooling systems around, up to 180 degrees Celsius, and they should be able to hold their strength at that level of temperature. I can again confirm with literature, like what is the exact higher temperature, but that's what decides the polymer. Yeah. The requirement for tapes, basically good tapes. I think I did a separate webinar. So having a good surface quality, smoothness is a very big factor in achieving good bonding, and a very uniform distribution of fiber and matrix. So there are no clumps of just fiber or matrix. Is, I would say, is a very good for the tapes. I've found, I think, so I'm not advertising, but Supreme tapes are, I think, very good in terms of um, quality. I've been also using from Bufa uh, thermoplastics. Yeah, 1,000 Newton tension is not conclusive. What megapascal are you talking about? Yeah, to be honest, it's I have only looked it from the point of view of like how much tension AFP is applying. I have not looked into from megapascal point of view, although it was the data is there. I'm sorry, I don't recall. But I agree with you. I think a better matrix is the megapascal. Yeah, it's your with tri-fiber, we can we can pretension them up to 25% of their given tensile strength. Yeah, for thermoplastic, you can almost go up to 90% uh, without breaking them. If there is no misalignment, you're able to tension them at a very high level, because they are basically cured thermoplastic strips. Um, so from me, I think this is what I've noticed, is that the tension can be very high. It's kind of one of the reason for thermoplastics to be used, as I mentioned But this is very good information, sir. That really thank you for sharing. If you're just using pure fiber, I would say even for prepregs, it should be about the same range than about 25%, because there also the resin is not cured and only the fibers are taking the load, and then it's not equally distributed. So, but yeah, I think um, seems these are our questions today. Um, as suggested, I would try to. Yeah, I think Eric is saying here, if the fiber is melted, I'm assuming matrix is melted, but not completely true, because you are not trying to. You're only melting the surface side of it, so the tape is not completely melted. It holds its shape. Um, so yeah, it's very high tension you can apply, because it's also for a very short duration. So I think that that's kind of what enables it to be applied, used with very high tension. But I think I might be wrong in this, of saying about 80%. But that's my, uh, just based on literature, what I found. I try to put this maybe in perspective. But yeah, I think just as mentioned in the, uh, I would say, just as mentioned in the submission form, I will have this recording uploaded in and shared along with some briefs, transcripts in a way, or like a brief of the transcript with everyone who has participated. I really appreciate you guys being here. It means a lot. I'm really happy to see more application getting developed in this area. Really appreciate it. Thank you, everyone. Have a nice evening. Bye bye. Okay, let's see.